Our project was on the dynamic analysis of an elevated water tower. So water towers, they can come in all shapes and sizes. As you can see, they're critical for emergency events because they hold a whole bunch of water. You can kind of estimate it as a whole day worth, or like 1 million gallons. And put that in perspective, a typical swimming pool has 15,000 to 4,000 gallons, so a million's a lot more. They are expected to stay functional in the event of an emergency, like an earthquake or a fire or something, to be used. And its design does require a dynamic analysis. For our analysis, they can be modeled as single lump mass systems, which was typically done in 1950s, and it worked well, but an earthquake in Chile in 1960, where some of the water tanks were destroyed and some weren't, kind of raised questions to researchers, and they decided to look into why this was. And in 1963, George Housner proposed a new equation where there are two mass systems and not just one. So for the single mass model, it's good for full water tanks where there's no room for any of the water to move or anything, or if there's no water at all. And for our model, we designed it as kind of like the golf ball on a tee with 2 degrees of freedom with translation and rotation. And we assume that there's uniform rigidity along the height and there's a fixed rigid base. For the 2-mass model, at any time the water in the tank can have any height. So as you can see, there's a free surface as less and less water goes in the tank. So Housner, then noticing this, came up with this kind of model where there's a mass at the bottom because it's assumed that at some portion the mass won't slosh. It just stays constant, so that can be lumped with the mass of the whole structure. And then the second mass kind of acts as a mass on springs on the sides as it sloshes, and it can be modeled like this. So more on that. Tanks that are put on the ground, some people try to improve Housner's model and said that an infinite number of masses can be used to help represent the water, but it can be like done Housner's way for elevated towers, and that's normally pretty okay. So for the single analysis, the single mass model, again, we had the 2 degrees of freedom, and we did it for 4 separate scenarios where it's 100% full, 80% full, 50% full, and 20% full. The rotation was not considered in the mass at the top. It was only the bottom mass had the rotation. It was analyzed as classically damped, and it had the multi-degree freedoms with free vibration.
So for our second mass, when the impulsive, the mass at the top comes in the picture, or the convective mass, we have to consider the stiffness contribution of that mass in the whole structure. That's how we did our analysis. Most of the things are the same, but we want to show the things that are different in this, which is the K2, which is basically, if you notice from the earlier slides, the K2 is basically a type like a Kn. The idealized spring that we have here, we wanted to convert that idealized stiffness to the stiffness of the whole structure, and that only shows, if you see the whole stiffness matrix, it only shows in the part that is related to the convective mass, which is basically given by this equation by Housner in 1963. The other parts are exactly the same as what we do for a typical 2-mass model, a cantilever beam with 2 mass at the end. It will be the same, but then in the middle part also we have some contribution of the first mass and the second mass. So we get this a typical scenario for one of the mode shapes. These are the other mode shapes that we have, but we haven't drawn here for the presentation. So this is one of the mode shapes that we did draw. And the equation for the K2 is given by this relation by Housner, and also when we do it for 3 degrees of freedom for the first mass, which is basically a body of water sloshing around, we do not include any rotational degree of freedom with that. But for the second mass, which is impulsive mass, and it's part of the concrete, part of the structure, we actually included a rotational degree of freedom for it, which is I1 given by a mass moment of inertia of a cylinder, and we have that is the whole mass for the impulsive, for the second mass, and for this one, and this is the mass of the empty tank, and this is suggested in the code that you can take 2/3 of mass of the supporting structure. Some of the studies actually says that you can take 100% the mass of the supporting structure and add it to the second mass to be very safe, but this is a very common way of doing it. So exactly the same as a single mass model, we did the same way. We analyzed it as a classically damped system with multi-degree of freedom and free vibration. We consider 5% damping. And since it was very difficult to analyze it symbolically, we actually came with some numbers. We considered a tank of 12 foot in radius and a supporting structure of 80 feet. And then we went with that and started analyzing our system. So that's the result we got for when we did it as a single mass, which we have the first degree of freedom is a displacement, and of course the second one was a rotation. And similarly, we did it for our this is when the tank is 80% full. We have the 3 degrees of freedom again, and the first 2 degree are the displacement or the translational, and the third one is the rotation. We want to show the last one. Okay. And this similarly, we have this for the 50% and also for the 20%. So to compare all of them, now what we find interesting here is that this is the one when we have it either like 100% full or 100% empty, because it's basically a mass sitting on the top. We do not consider the fluid behavior in the tank, and that's the behavior we get. And this is the behavior for 80%, and this is the same behavior for 20%. If we compare these three graphs, we can see more or less a similar behavior. This is like kind of inverse of that, but the whole behavior of the response is more or less the same. But now when we consider the 50%, which the water here has a lot of space to slosh around and bounce back and forth, and the one portion of it exactly acts like the model the Housner represented, we can see that this portion actually start dumping better than this, and this more consistent looks like the 50%, and it actually starts. It damps more than the two situations when we have 80% full and when we have 20%. So these two are behaving like that's full, like 80%. We can say that behaves exactly like if it was 100% full, or 20% behaves like if it was like 0% full or 100% empty. But this is where the effect of the water comes into picture. We can see that it's more. We can see some damping here that could be when we idealize those springs, when they start moving, they started dumping some of the energy. If you think of it as water, we can say that since the water moves, we got it like in the forms of tidal or wave energy that dissipates. We can somehow see those relations here. And of course, the similar behavior is also repeated in the second degree of freedom. We cannot compare this with our single mass model, because in that the second degree of freedom is a rotational degree of freedom. These three are still translations, so we can see a similar behavior. These two are the same, and that one is different, and it fades faster. But to compare the translation, which was the second degree of freedom for the single mass, and this is the third degree of freedom for the other three masses, we can see a similar behavior, which we can also state that if in the text, if you notice, they do not really consider the rotational degree of freedom for the structures. When they do the analysis, but for the mass moment of inertia, they just consider 0 and 0. So probably is because they don't really make much of a difference, and that's what we thought. So in conclusion, we can say that a single landmass model is not applicable for all cases because the best behavior would be to consider different heights of water in the tank to analyze it to be more representative. And what we did, the whole analysis is based on a free vibration. If we have a different excitation, like a blast over pressure and everything, those results might change and we might have different behavior. And also the soil structure interaction plays a very important role. We did that a little bit, but we found that our results didn't really work well, and that could be because we didn't know at the beginning, but since the last lecture, Professor Shinton explained about the limitation in the height and everything, that because of it, because we consider like 80 feet tall column with some 20 feet tank on top of it, so it's like 100 feet structure. We couldn't just simply ignore the soil structure behavior to do the base shear and base overturning moment and everything. So that's very important also. It should be considered in the analysis.
I was wondering in those near the end, the results that you were showing with the 4 graphs. Yeah, go back to your first set of those. Was that the first one?
Yeah.
So on the upper left, and this is free vibration, the tank empty and the tank full.
Yeah.
You've got a different mass, which to me is going to say a different frequency.
Oh.
And I guess I'm not. Why are they the same?
This is only for the tank full.
Oh,
but it could be the same behavior, only a different mass.
okay, right. So,
Yeah,
but
so
if you actually
we
plotted both of those together, you would see 2 different curves.
This is only for the full tank.
I see. Okay. Do you know under what scenarios you got the greatest? And you probably may have shown it, but the greatest movement of the liquid, of the fluid sloshing.
Let's say 50%.
50%.
Yeah, but it's also interesting to see that in the 50%, the behavior is much more. I mean, we say it like consistent, and it also the amplitude. The magnitude of those values are smaller than the. In a way, it says that the water, when it starts slushing, it dumps. It probably helps in the damping, because we assume the 5% for all of them, but as you can see, this one by 30 seconds is still the same behavior, but this one by 30 seconds are almost dying out.
There are actually systems that have been proposed that are called tuned liquid dampers, and so you can actually create a damper by that concept, and it could be a very simple and cheap, inexpensive type of damping mechanism, but basically, and they've been developed and researched, and a lot of them have gotten very complicated, but the fundamental idea is just what you've described there, is that you have a container full of liquid, and when if it's moving, then it's going to, it may counteract some of the motions, and if you tune it by adjusting the height, the volume of liquid correctly, and it depends on the geometry of the container and all that stuff, you can tune it to get the type of behavior, to reduce the behavior.
Yeah, we try to look into that, but they mostly try to tie it to the tidal energy and how it dissipates, so it became very complicated, and also we only did this for a cylinder, and then when the shape changes, everything changes.
Well, I actually had a student 2 years ago for the class did his project and built a little model that had a little tuned liquid damper on it. Okay, great.